Hello everyone, my name is Mauricio Gonzalez and I'm going to present to you the work that Jorge Silva and I are presenting in the IEEE International Symposium on Information Theory 2020. We are from University of Chile and the title of our paper is Data-Driven Representations for Testing Independence, a connection with mutual information estimation. So here is the outline of the presentation I'm going to do right now. So we are going to start to the motivation of the problem we want to tackle. What we want to do is to detect independence from independent identically distributed samples of random variables x and y. So the question we want to answer is that given samples of these variables, and without knowing the underlying distribution, are x and y independent or not? So this is not a new problem. In fact, it is a fundamental problem in statistics that has numerous applications in data analysis, inference, and decision problems. A natural strategy to tackle this problem is to partition the observation space, as we can see here, to evaluate the discrepancy in some sense between two empirical distributions. So there are some previous works that are based in this strategy, like the histogram-based approaches, and other works that are not based in this kind of partition schemes, like the kernel-based statistics. The one I would like to highlight is the log likelihood statistics, which is a method that is based on this kind of partitions. And I want to highlight this because it's the one that we are going to use in this work. So if this is a method that has already been used before, what is new in our paper? Well, we propose to explore the role played by data-driven partitions because, as we can see, we have the same data in these two figures. That's very clear. And it's very clear also that there is a statistical dependency between these two variables. As a matter of fact, there is a positive correlation between x and y. Now, in both these figures, we have made partition that has 16 bins or blocks each. In this case, we have a non-adaptive partition, which is a product partition. And here we have an adaptive partition, in the sense that it concentrates more blocks where we have more higher concentration of the data. So it is very clear that this adaptive scheme is a better representation of the data than this one. So the partition that we use is relevant. It is not trivial. Another important fact about adaptive partitions is that under the hypothesis of independence, the trivial partition, which is the partition with just one block, is a sufficient representation of the problem. Because, as we can see here, if we have independence between x and y, then there is no tendency that we can see here, as we could see right here. And as there is no tendency, then why should I make any partition on this space? The trivial partition, which is just one block, should be a sufficient representation of this. So a well-designed scheme should have the ability to detect this trivial solution from the data itself. Before formalizing the problem and defining the variables we are going to use, I would like to highlight the contributions of this work. First, we propose a strongly consistent test of independence that is inspired by the Neumann-Pearson test. Secondly, we establish a clear connection with the problem of estimating the mutual information between two variables using samples of them. And finally, we give some results about structural detection of independence, which is related to what we mentioned here. Okay, so in order to formalize the problem, we will give some definitions. First, we will start with probability measures and divergence. We will denote by P and Q two probability measures in this space, and we will denote by Greek P any measurable partition of the space, and where this set can be finite or numerable. Then we define the divergence of P with respect to Q restrict over the events of P, given by this expression, as we all know. And the divergence of P with respect to Q will be the supreme value of this quantized version over all the measurable partitions. Next, we define random variables x and y which takes values on RP and RQ, where P will be the joint probability of the concatenated version of X and Y. This random variable will be denoted by that, and of course it will follows P. And we will consider samples of that, which are IID, of course. So the objective is to decide whether X and Y are independent or not using these samples of that, but without knowing the underlying distribution P. For that purpose, we will use a decision rule of length n that will take n samples of that and will return 0 if X and Y are independent and 1 if they are not. The next definition, we will say that a decision scheme is strongly consistent for detecting independence if for both hypotheses we will reach the right decision eventually with probability 1. So graphically, that means that, for example, if we have independence between X and Y, and we represent here the number of samples in a logarithmic scale, and here the decision rule, which can take values 0 or 1, then when we have few samples, the decision rule oscillates between both decisions, but once we have reached a sufficient number of samples, it reaches the right decision, in this case is 0, with probability 1. And the same goes for the alternative hypothesis, it would reach 1 eventually. So now we are going to share the proposed test. With that proposed, first we use this notation Q asterisk to represent the product of the marginals of P. Of course, Q would be the true distribution in the case we have independence. So our approach will be a two-stage process that uses these samples twice. First, we will construct a partition of the sample space using these samples. And we will use that partition to estimate P and Q and construct empirical versions of them. Using those, we will compute the empirical version of the log likelihood statistics, and we will compare it with a threshold A sub n. And based on that comparison, we will decide if P is equal to Q. In that case, we would have independence, or if they are not. So the decision rule will be an empirical version of the Neumann-Pearson test where we compare this statistic with the threshold. Now the statistics denotes the empirical log likelihood statistics, which is given by this expression. Note that we use the empirical distributions here, and it is projected over the cells of the partition. So here's the notation. The empirical distributions correspond to the number of samples that belongs to each block divided by the total number of the samples. So in order to determine the quality of this test, we will compare our statistic with the statistic we would have if we know the true probabilities, which is the Oracle test. So we'll introduce the true likelihood ratio, which uses the true probability distribution. So it's like the Oracle version of our empirical statistic. And we will introduce the regret as the difference between this true likelihood ratio and the empirical version. So note that the difference here are because of two factors. First, we have the quantization effect introduced by the partition. And second, we have the fact that we are using empirical versions of the distribution. So in order to analyze this difference, we will introduce like the intermediate step, which is the Oracle quantized information, which uses the true probability distributions, but restricted over the partitions, over the events induced by the partition. Now, considering this, we have clear relationships between our statistics and terms of information. In this case, is the empirical versions of the divergence, quantized version, and the divergence itself. And note that the true likelihood statistics converges almost sure to this divergence, which is the mutual information between X and Y. So we can decompose the regret as these three addends. And what we would like to do is to minimize this over the partition we will use, because that's the thing we can control. Now, note that the first term, we can't do anything, but at least we know that this converges to 0 almost surely. So almost sure, so there is no problem with that. what we can do is to minimize these two items here using the partition. The first one, we will call it the approximation error, which is due to the quantization effect of the partition. And the second one is the estimation error, which is due to the fact that we are using empirical versions of the distributions. So we have established here a connection with the problem of estimating mutual information, because we try to minimize this. So we can use the results from this paper 12 that you can read, of course, if you want. I recommend you to do, where mutual information estimation problem is addressed using regularized tree structure partitions, which is a way to represent these partitions as binary trees, where each leaf represents a block of the partition. And once we have a full tree, we regularize it in order to find the optimal trade-off between approximation error and estimation error. So one of the results we can use from this paper is that we can bound the estimation error. In this sense, we find a bound of the estimation error that just depends on the size of the tree, which is the size of the partition, and does not depend on the underlying distribution. So what we will do is, as we don't know these true probabilities, we will minimize the approximation error and the bound of the estimation error, which is expressed here, and we call it the infomax problem. But again, we don't know these true probabilities, so we will use their empirical versions. So this is the problem we will solve, and from here we will obtain an optimal empirical tree. Okay, so we are going to use this optimal empirical tree in our main results. The first of them is theorem 1. Of course, if we have this tree, we have a partition associated, and we will use this partition to define our decision scheme. So under these conditions, we have two separate results for each hypothesis. The most important one is for null hypothesis, because what we have here is that with high probability, the regret will reach 0 for a finite sample size. Now, we know that this true likelihood statistics is always 0 in the case of independence. So what we're saying here is that our statistic reaches 0 in a finite sample size. Now, the way to prove this is, and you can see the detail on the paper, of course, but what we do is to prove that our scheme eventually reaches the trivial partition. And graphically, we can see that here. Here we're plotting the tree size, which is the partition size, and we can see that this eventually reaches the trivial size, which is 1, of course. Okay, and under the alternative hypothesis, we don't have such a strong result, but we have a bound of the regret, which is constructed as an optimal trade-off between the approximation error and the bound of the estimation error for the oracle test, because as we can see, we're using here the true probabilities. So our solution nearly matches the performance of the oracle version with high probability. Okay. Next result is lemma 2, which is the consistency of the regret. And basically this tells us that under both hypotheses, we have that the regret converges to 0 with probability 1. Now, what is more important here is that if we have independence between x and y, then not only the regret converges to 0, but it does at a super polynomial velocity, in the way that this is faster than any polynomial. Now, remember, this term, the true likelihood statistics, is 0 in the case of independence. So what we're saying here is that our empirical statistic converges to 0 at a super polynomial velocity. So if we compare here our statistic, which is the empirical true likelihood statistics, and compare it with a polynomial, in this case of grade -1, we can see that for few samples, this can be rated, okay, but eventually this will converge to 0, and it will thus at a higher speed than this polynomial. So this gives us a criterion to define the threshold, and that is what we use in theorem 2, because if we define the threshold as vanishing at a polynomial velocity, then we obtain the strong consistency of the test, in the sense that it will reach the right decision eventually with probability 1, as we have defined it before. Okay, so those are the main results. Before finishing the presentation, I would like to give you some take-home points. So We have derived a data-driven test of independence, and we give sufficient conditions to obtain a strongly consistent test. Also, we establish a clear connection with the estimation of mutual information. And finally, we give some results supporting the capacity of our scheme to detect independence, in the sense that our partition scheme collapsed to the trivial partition. So right now, we are exploring further structural results for detecting independence and to reinforce this idea. And also we are making some experimental validation in order to compare this test with other tests that do not take advantage on the structure of the partition or do not use adaptive partition. So we are working on that right now. So that's it. I would like to thank you for watching this presentation. We also encourage you to read the full paper in order to understand with more detail all the results we have presented here. So that's it. Take care and thanks for watching.